Okay, let's start the next session. The next lecture is on design, development, and the properties of organic semiconductor. So in the previous lecture, I said I give the good um, introduction about what is organic electronics and their application, and also I said for any devices, any application, we need to have the right material. Then only we can get the application of properties of what we want. Okay. Now I am going to give some overview about how we can design the material and what property we need to consider when you design the material. Okay, it's all a little bit about chemistry because everything about molecule is basically start from chemistry. It's more into organic chemistry. Okay, I'm not going to talk about any synthesis. What is the design criteria only is something is physics oriented. I'm not going to finish how the synthesis method and Suzuki coupling are still not that type of chemistry. It's just a design category. It's like material chemistry in aspect. Okay, so it will be interesting to know how the property can change. Okay, so we are going to do design and development. In this, okay, this slide shows some of the library of different organic semiconductor. Okay, when this field start, the very first material is sort of the pentacene. Because why this is called pentacene is I give the name here. Penta means 5. You know that. Is it the benzene rings are fused together? It's called pentacene acene structure. If you see this one, as I said from my last class, if you want to have delocalized orbitals, if you want the electron to conduct, it's delocalization. Then we need to have a conjugation. Conjugation means single double bond or triple bond is alternative. If there is not any alternative, if it is not like that, then material won't contact. So you should remember there should be a conjugation should be there in all conducting organic material. Okay. So in this material, all this material is conjugation. You can see. So this is pentacene. If you see I'm giving the band gap as well because this designing criteria overall how we can get the required band gap as well as how to control the homolumen. Homolumen in a sense, I'm saying valence band, conduction band. Because depends on valence band, conduction band, then we can say how to inject electron and how to extract electron from that. In those aspects, homo level is also important, same as what band gap. You know, band gap is give the things, what energy it absorb, what energy it will emit, those type of things will band gap will control. Okay, so the pentacene will give around 2.2 eV, and rubrine structure is only 4 benzene ring with some side benzene ring, but this will somewhat increase the band gap. You know, it is going down, is going increasing. And CBC copper thiocyanin is another material, is the p-type material. You can see the band gap is reduced, and you can see the structure is somewhat a planar structure. So, and if you say all those things, all the HOMO level is around 5 something, and LUMO level is around, particularly if you see BT benzodiazepine, this band gap is very high, 1.731. This structure is benzene something different, okay? And in the right hand side, if you see that after PCBDT, the fullerene is well known as an acceptor material. It's based on carbon allotrope, it's acceptor. If you see all this right hand side, whole things are acceptor in the sense I am talking about is N-type material. In the N-type material, if you see all the HOMO level around 5, but all the acceptor is HOMO level is below, still further down. That means for N-type material, for P-type material, the HOMO level is a little bit higher. Higher means is the HOMO level is lower comparing to the acceptor is lower. Something you got to see, this is HOMO means the acceptor. This is the size you can see. If this is level is up, something level down, we can accept a material. So that it will be useful in making a device. The electron can be easily come down to the HOMO of the p-type material. That I will explain later. If you see the whole trend is this, if you see this one, and if you see this one, all things are step down, one step is down. So this is a design kit. This is a HOMO level requirement of acceptor, donor and acceptor. Donor level, if you say this HOMO is higher, HOMO is lower, for acceptor, HOMO is lower. Both things will come down. Okay? Sorry? No, I am giving this is a reference level, not the whole thing. It's not all everything is different. The 4.6 is lying here. Out of this, where is going up and down? Because this 4.6 is for me, anything is good. Any level, any material is HOMO level is still less. That compound become unstable automatically. So that's it. So we need to take care of those things as well. And this one I talk about the energy level of semiconducting, inorganic and molecular semiconductor already. And if you see that the whole entire electromagnetic spectrum, so this is X-ray is a very high energy, and next is UV, and this 100 to 200 to 1800. This is a visible region here, ultraviolet, low, and away, and infrared. This is a whole spectrum up to infrared region, and this many material will absorb in this range. And more importantly, I am giving the input solar radiations, okay? Because normally when you have the organic photovoltaic, this is the radiation you are going to absorb. So 2.5 is 2.5 micrometer. This is all infrared range. Then going down, infrared is a low energy, but wavelength is high. You know that if the wavelength is low means frequency is high. If frequency is high, energy is high. Okay, it's a higher wavelength means low frequency, and this is all low energy, and go towards. This is your around 800 to 300. This is your visible region. Okay, so in this visible region, your silicon is band gap is 1.5. 1.5 is come around 1100. That's why the silicon it start absorbing 1100. You can see that the band gap is play role where your material is going to absorb. If it is 1.1, it start absorption 1 point, because the band gap of silicon is 1.1. Correspondingly, if you calculate what is the wavelength of, I will tell you what is the relation between the band gap and the absorption, the wavelength range. Next slide, I will show you that. So it's not 1. So which one? Voice not proper, is it? Okay. Now it's okay. I think I know. Okay, this is solar spectrum. Okay. This pic. Hello? Yeah. Hello? Hello? No, it's, hello? Is it okay now? I think so. Okay. So for a OPV device, if you want to harvest required, because ultimately we want to harvest all the whole solar light. So I'm telling example, the existing cell is silicon. Silicon is 1.5 band gap. The corresponding 1.5 band gap, the wavelength is absorbed is 1100. It's 1100 something here. So that's why the silicon will start absorbing light, all those things, and it give the efficiency of 20%. Suppose if you design the molecule as around 1.5, then we can harvest all those light. So how we can get the 1.5? If you start from all this, anyway, if you go beyond this one, is all infrared radiation, and it is very small. Only this energy range is only we have a very high solar light influx. Okay, comparing to all those time. So basically, we concentrate only how to harvest all these things. Silicon is ideal. Okay, even. So how we can design appropriate level? So before going to this one, and also this will have some photophysics. The photophysics, if you see this one, I hope you understand this Jablonski diagram. So any level we have, the ground level is S0 and S1, S2, those level will be there, high level. So when you absorb, when you give the energy, it will, any molecule if you give the energy, it will absorb to the higher energy. At least the minimum it go to S1, S2 level. This is called absorbent. And the number 2 process, then within the S1, S2 higher, in the excited state, it will relax to the minimum state, then it will emit light. Then it will come to ground state. When it comes to ground state, it will radiate, emit energy. That will come as a fluorescence, okay? Sometime this one go to the intersystem crossing and go to the triplet state. So you know what is singlet state is, the spin is all one minus of minus plus of is becomes 0. But in the other triplet state, the spin is 1 actually. Is it the spin will turn around. So it will go to the triplet state, then again come to the ground state. This is called as a phosphorescence. Phosphorescence is nothing but it's a delayed fluorescence, okay, something like. So again, this is intersystem crossing, and this type of process is quenching. Quenching is nothing but without any radiations, and this is sometime that the material will come to the phosphorescent triplet, it will again go back to the singlet state. This is a reverse intersystem crossing. Sometimes the energy level match is very similar to the singlet one, and triplet level it can go back to the singlet, and again it will come to the fluorescence level. So this type of material we using something, the latest one, TADF material that I will talk to you later. That is the thermally activated dyeing material. Okay, so this is some of the photophysics process. When you go to the device fabrication, we'll understand more about this process. Okay, if you want to design a new organic semiconductor, we need to consider this much property, at least, because the whole point to work on this organic semiconductor is it should be soluble in some solvent, because some material, if there is no side chain or long chain, it won't be soluble, because not all organic material is soluble. Depends on what functionalities of what we are keeping this molecular design. For increasing solubility, the side chain, alkyl side chain, we'll put it that one, that will increase solubility. So we need to have appropriate amount of alkyl side chain, and then we need to consider mobility. So mobility come down, we need to include all the pipe stacking. We need to have some type of regular arrangement. When you coat the material, it should automatically self-assemble into crystalline structure, somewhat crystalline. That will help to improve the mobility. And also then high molar extinction coefficient. That means it should be high level absorbing light, very high. Absorption coefficient should be very high. And another one is we need to have control of band gap, and we do have a long-lived exciton state, because it's all everything talk about is exciton. Even if you want to harvest the light, the first stage is exciton is created. That means hole and electron bound charges. After that, if the exciton live for a long time, then only it can diffuse to the donor acceptor interface, then it will separate out. If the diffusion, if the state is if only the short-lived species, then it will recombine and it will become waste. It should be long-lived one. So all these criteria we need to take care of. Okay. So can we design the molecular semiconductor? The material design itself. I will tell you which part will increase the solubility. Okay. So required band. So this topic is somewhat called band gap engineering. Before going to the design, we'll tell you how to calculate band gap, as I said, and the homo-lumo. Suppose if we do some characterization, I'm going to explain what characterization. From that characterization, how we can get this one. Okay. Yeah. We see this. We know all the famous formula is E equal to h nu. You know that this energy formula. Nu equal to nothing but if we know what is speed of light, c equal to lambda nu. That we know that. From that we know nu equal to c by lambda. So that is well known. So this equation we can write down in this one. Then if you simplify this equation, you can h constant is 6 × 10⁻34, and c is 3 × 10⁸, and we saw what is h at 1.99 is joule meter. Okay. Normally, when you do the all band gap, we will represent in terms of EV, electron volt. If you convert this joule meter into electron volt, you will divide the whole term by 1 electron volt. What is 1 electron volt? It is 1.6 × 10⁻19. That's called 1 electron volt, right? If you divide by minus 119, that means minus 25 minus 19, then we'll get 1240 nanometer level. Okay. Remember, because this we are putting in nanometer. Okay, this one. So all all those things, this h nu term is 1240 and divide by lambda. You can remember this formula. If you have a, if this wavelength is lambda is 1240, 1240 divided by 1240, then your band gap should be 1 eV. So if you put 1240 by 1100, that was silicon 1. 1240 by 1100, your energy, that's band gap energy, nothing but that's why we are getting here is, if I see is the previous slide, I said 1100, right? So 1100 where you are coming, if you put lambda is 1100, roughly 1240 by 1100 is equal to 1.1 volt. So that's your band gap of the material. So where is coming from this lambda? You go to calculate where absorption start. Suppose in case if the absorption start at 620, is 620 is just as half of 1240, then your band gap will be, no, 2. 1240 by 620 is a 2 eV. Okay, like this, if you know the wavelength of onset of your absorption, then you can find what is the band gap. This called another way you call optical band gap. This way. So the band gap is low, then your absorption will be extended. That means you will extend the wavelength, higher wavelength absorption. So that will be the required point. Okay. Any question? This is a very important point because we will be doing some of the tutorial work based on this one. Yeah. Which one? Yeah. Ideally, if you want to harvest energy, we need to extend the range of spectrum, right? So if you want to extend the range, then it should 1240 or 1300, 1400 like this. If you want to extend means your band gap should be very low, right? Suppose band gap is 1100, right? If you want to, but ideally it's not possible. It's very difficult to go below 1 eV. Then your VOC will be very low because I will come to the VOC concept. You know what is open circuit voltage? If you're very low, then VOC also get low. We need to have a decent open circuit voltage to get a required power output. Okay, we can't reduce too much. So in this, this is one of the famous donor polymer is poly 3XL thiophenes. In this one, I'm saying that we can find the absorption spectrum in 2 ways. One is we can dissolve the material in a solvent, and we can solution phase we can find absorption. And also another thing is we can coat it a film and solid state we can dry it, then you measure it. There will be different. Structurally both are different because in solution state everything will be loose and everything will move around. In solid state it will have self-assemble, it will have the regular arrangement will be there. Those things will affect the band gap as well as the absorption of things. You see, this is the block line is solid line is this is solution absorption. This red curve is a film absorption. You see, the absorption is extended. So this because of this one. This one. Yeah, this is not broadened because I'm giving the x-axis up to 7. This is 900 when you extend it. No, both are same thing. What I am showing here is this is a solution, this is a film absorption, this is a film crystal. When you make a crystal is yeah, this because of the because both are entirely different form. One is solution form. Solution is arrangement is it will be loosely bound one solution one, but in film state it's the regular arrangement is there. That will improve your absorption. It will and also it will extend the absorption. That is the problem. That's why it's all depends on how structural things. So if anything things any molecule, if you take it as a solution process in the solid state, the absorption will be different. Okay, but normally we need to. Many people report only the solution absorption, but our purpose that's not right. We need to take absorption in solid state. So because your device will be in solid state, we need to appropriate, correct? So this one, crystal may not be possible because some organic molecule, if you leave it in a solution, slowly evaporate, it can self-assembly, it can form crystal. How the sugar is forming? Sugar they will dissolve, make a concentrate, they leave it, it will make crystal. Otherwise it will be powder, right? With the crystal form, it looks like everything, the arrangement is different, but if it is leave it, if it is dissolved, then the structure is different on the solution form. Okay, so this absorption will be different with the different state of the material. Okay, got it? No, this is absorption. No, that is two things. One is absorption, other one is luminescence, photoluminescence, PL's technique. So this is only absorption. So luminescence will take where is absorbed. If you surround, if you have 550, then we excite a molecule 550, then it will say where is emit. That is called photoluminescence. Okay, this is absorption spectrum. And this is a PLO, the red line, right? The dotted line is called PL spectrum, photoluminescence, because normally they emit at a lower, because normally we don't, when you excite with the higher energy, it emit only lower energy. So that's why you can, right hand side is a lower energy, okay, higher wavelength, this emission spectrum. So if you give this is an onset absorption, because if the onset is starting like this, if you draw the tangent like this, like here, so where it's cutting the tangent, so we can say that this is something 650 is surrounding cutting. That's why I take 650 here. Okay, so 1240 by 650 is 1.90. That's a band gap. I hope you all understand how to calculate the band gap from the onset of absorptions. Is it good? That's where it's starting absorption, because that itself the material start absorbing. That's a band. We need to have the first absorption, the first one, because ideally this type of material is a broad absorption will give. Sometimes depends on maybe two band will give. So where it start absorption zone, first one. Okay. Yeah, depends on where you are applying. Okay, majority. That's why in the morning lecture I said how to, all the CV is solid state. When you have the things, I said another graph, how to convert it into the vacuum level. Yeah, we had added the term is 4.8, that's called, that's fine. So that's one we need to standardize. So we always use ferrocene as standard internal, that's called 4.8, then we need to add. I'm also going to talk about other things, okay. This is called optical band. This one will tell you about only band gap of things. It doesn't tell you where is HOMO and LUMO. How to find what's a HOMO. HOMO, LUMO means nothing but is a valence band, conduction band in terms of inorganic. So those things we can get it from CV. So CV is a 3 electrode system. One is a working electrode, other one is a counter electrode, then reference electrode. Normally in these measurements, the reference one we use AGCL. Ideally we need to use hydrogen electrode, that's a 0,1, but normally we count it, normally AGCL, then we convert it into standard hydrogen electrode. That's why we use the conversion factor. So he used a ferrocene as a standard for this one. What is it? So here what we are trying to say, this is the highest occupied molecular orbital. This nothing but is a valence band, this LUMO band. In between the difference between the highest, the HOMO and LUMO, it's nothing but is a band gap here also. So here we can call it as a electrochemical band gap, this one, but what we saw in the previous one is optical band gap. It should be equal, but in all the case, it won't be equal. So for band gap wise, we will consider from optical band gap. HOMO, LUMO, we'll take it from here. This one is an easy process, but the exact way of determination of this HOMO, LUMO is UPS spectroscopy, this ultraviolet photoelectron spectroscopy. That is only giving the exact value, but that instrumentation is not everywhere is available, it's very expensive. But this is the one easiest process to find out, because if you synthesize more organic chemists, because UPS always handled by the physicist, only the experienced people, then is a high cost instrument. So the people prefer using this instrument, okay. Here this is the formula used, HOMO level is 4.8, because this one we use reference of silver electrode, so conversion to 4.8. Then what is oxidation? Where to find this oxidation? For example, if this is a reference CV spectrum, normally where it starts from here, it's from 4 to 0. So when you do towards positive, it will going, this peak is called oxidation peak, and again it called reduction peak. So this is CV voltagram for ferrocene, okay. So ferrocene, to find the oxidation potential, we find a tangent line here and the base line. So this point is your oxidation peak. Like this, for reduction peak, you need to find where it start ejecting this one, and we need tangent. So this point is your cathodic peak. Okay. So like this, we need to find oxidation peak, reduction peak, and we use this formula to find out what is in HOMO and LUMO. So I hope you'll understand. You note down this the value. So when you do the tutorial question and next hour, you will understand more about how to calculate. I think. Any questions? No. So I said this is answer or oxidation, right? Well, starting is plus. After that, now when you get a reverse voltage, then it will go to this is a reduction. This is a reduction potential peak, but we need to calculate this tangent, right? And this is a value where it's starting. This point. So this point is your reduction potential. Okay. For oxidation, the point is here, the onset. Okay. Now we come to the design point. Yeah. That's already standard design using ferrocene in this one, yeah. Because last time people used, sometime previously we used the standard hydrogen electrode is 4.5 we calculate, but that's a long back. But now the correct one 4.8, but some research groups said it's 5.1, but I don't see. There are different ways that we can find the literature, but we fix it around 4.1, anything, plus your oxidation and minus of reduction. To 4.8, normally HOMO, if you add up the oxidation, normally it will be plus 4.8, something 5.5 it will come. When you come to the LUMO level, with 4.8 minus some value, if you do minus 1, it will come 3.8 something. So that's a LUMO and HOMO level. Okay. Good. Yeah. No, ferrocenium reverse. This is for any other material. This is 4.8 is a reference only ferrocenium. Suppose, for example, that's why I will going to give the question. Suppose P3ST, if I say that the oxidation potential you are getting like somewhere is 0.7, then HOMO will be 4.8 plus 0.7. How much you are getting is around 5.5. I'm saying this is a formula used any material you put it inside. Any other material, either it's P3ST or any other PCBM, whatever you getting this line, you don't worry about any other thing. Whatever the oxidation potential, the onset you are getting, add this one and reduction potential this one. Normally reduction potential you will get in the negative range, so minus, okay. Okay, now we do the design criteria. For example, I'm saying the one example, this is organic molecule like this, something thiophene, and next one. This actually is three-dimensional picture. Suppose when you come to this thiophene and this thiophene, it looks like twisted. You know that why is it twisting means it's some of this then the structure is some again is become there. This our torsional twisting is there, and also if you see consider this one, when you have the CC double bond, we know that the bond length between the CC is 1.54. If you have double bond, 1.34. If it is triple bond, the size is 1.2. Okay, so this type of the difference in the chain, that's also impact in the band gap. One thing. So one thing is only the chain, the bond length is one of the factor. The other one is conjugation length. So and also when you have the two bond, double bond and triple bond, the conjugation length is different. And also when you increase this type of number of unit of this thiophene in it, if you have a 5 thiophene, 6 thiophene, 7 thiophene, like this in the molecular structure, according to how much thiophene the conjugation number is increasing. So that also will affect your band gap of the material. The third one is functional group substitution. Suppose this in this molecule R is a functional group. This functional group can be electron rich or electron withdrawing group. Electron rich means amine group or sulfur like this. Electron withdrawing group is CO2, the oxygen group, and some of the electron accepting group. Then we can that will give some of the example. What are the accepting group done? So that will change your affect your band gap of the material. So other one is interchain effect, and this is I'm saying R is a alkyl chain. By putting this alkyl chain, we can increase the solubility. Last time you were asked the question, how increase the side chain? So this is a value. We can't, alkyl chain normally is insulating, it's not conducting. Alkyl chain can be one. Only the backbone only we need to make sure it should be conjugation. But other side chains can be anything insulator. That will increase the solubility of your organic semiconductor, okay? And this is a side chain. That side chain effect will affect how the molecule is arranging in the solid state. That also influence. So then interside chain effect. So all these are very necessary factor for the molecular design. Some of the other factor, bond-length alternation and induction effect alternation, because when you have this substitution group is more like electron donating or electron accepting group, the effect is called induction effect, because of this electrostatic static attraction between them, some of the electron move towards, if it is an accepting group, it will going towards polarizing towards accepting group, then we can have some type of dipole orientation. So this dipole changes also create impact on the band gap of the material, okay? So now I'm going to see each one is one example. For example, there is another design criteria is donor acceptor concept. The other one thing is because we know we have the donor is more electron rich, acceptor material is more electron deficient group. By making this type of polymer, donor chain acceptor, donor acceptor, if you have like this effect, then both will be like act as a push-pull effect. One is donor and accepting, one atom is like pushing, other one is pushing. If you have electron rich group, it will push the electron out. If electron accepting, it's pulling the electron out. This type of push-pull effect we can introduce into the donor acceptor based molecule. So that will have the great impact on the how to control the molecule. So this is another type of molecular design, okay? So this is some of the example. If you have only the benzene ring, this polyparavinylene PPV benzene ring, this have the very high band gap of things. Because, so this one have phenyl group, there will be a steric interaction will be there, it will be better. So there will be a twisting in between the phenyl and phenyl group like this. So that's why the conjugation will be slightly affected. That's why the band gap is very high in this one. But in this PQS molecule, on top of this benzene, we have the more acceptor-like zinc group that will slightly decrease this one comparing to this one. The polythiophene is somewhat more on conjugation group that shows a very low band gap of 2.0. And we compare all those things. In this one, we have this thiophene, and when you put the phenyl group on top of this thiophene, the band gap is too much reduced. This is because of the resonance effect. So resonance effect is nothing but there will be a change of double bond and single bond. So for example, if the phenyl group, you understand what is the resonance. If this double bond is changing to next position, something it will be resonance from this position to other positions. Like this, it will be resonate each other. So that will create your like quinone group, something. If benzene will become easily quinone when the double bond is changing. The quinone group cause very low band gap of this material. Okay, so like this, different structure will got different. So you see, these are all polymer material. It's not only one side chain; it will be repeated chain. Okay, so before going to that one, I just giving little bit overview about how this HOMO level is. What is mean by HOMO level? What is bonding and antibonding? We talk about it from atomic level. In the atomic level, if you see the frontier orbital, we take it example is a hydrogen atom, very simple atom. So the hydrogen atom, so is always electron is moving around the hydrogen atom like this. Suppose if you have two atoms together, like this in this case. So when the atom is coming here and this also coming here, the interaction will be more in that case. Okay, then it will be combined together. That's called. Then the wave function is moved together. That's called bonding effect. Suppose when you rotate together, it is go away from the like this. That's called anti-bonding effect. Okay, this means the atom is going away from each other. It won't be much interaction between this atom. There means nothing, empty level. This is so in between. There should be a level. So in between one, it's more together. Some type of when you go from this bonding to anti-bonding at this level, it's where that's called node. That place we can't find that atom. The probability of finding the atom in that position is 0. That's what called node. I think here you can bonding and anti-bonding means when the when in single atom, if it is, when it rotates down, it's coming together, it's called antibonding, it's electron interaction mode. It is far away from here, this antibonding. So when you have a multiple atom, this interaction will be multiplied and it will create a bonding, antibonding multiple state. For example, this is bonding, this antibonding. This is for 1, 2 molecular atom. If it is multiple atom, this bonding will be more and antibonding will be more, and it will make a continuous level of this structure, and you have a band structure like this. Okay, if you see the next, and also this is a basic of your sp3 hybridization. So normally s electron this one, and p electron 6 electron. You have px, py, pz. Each orbital have a 2 electron, totally 6. So when you have the sp2 hybridization, the px will hybridize this one x-axis. It will form a sigma bond, but only the sp2 hybridization, only z-axis one. Sorry, the x-axis one here case no bonding, but that pi bonding will interact. Will interact and form is a pi bond. Okay, so this pi bonding only, the interaction between the pi bonding only make electron delocalize, it make the conductivity. Okay, so this is some of the things I also explained this one morning. This ethane group, this is sp3 hybridization. This is almost insulated. In this ethene group, sp2 hybridization have that extra bonding will be there, make a pi bonding. In sp hybridization, we have 2 different pi bonding, because in sp hybridization there is only one sigma bonding, remaining 2x, px, py will be empty bonding. Those empty, though unhybridized, sorry, is not unhybridized orbital, will make delocalize the electron. So this will make a 3 bond, this is 2 bond, and this is 1 bond. Okay. So this in these two cases, so unhybridized p bond will overlap and sideways and make electron delocalized. Okay. So you remember these 2 points. So if you consider the somewhat complex, previously considered for the only for hydrogen atom, very simple. Now is a molecule CH2 and CH2 both are involved. So in this case, in the sigma bond sp2 hybridization, sigma bond is very big because it's very tightly bound. But in p bond is delocalized. That's why the energy level is here is very less, HOMO level. If you see this sigma bond is very high, and this T HOMO and LUMO. Now you can understand, if I say HOMO means you got to imagine what I said is a bonding. If the LUMO level is similar to what is antibonding, whereas atom is different from each other. Okay, so in that case, the bonding means this orbital is come together. The antibonding means both are in different direction. So where we come out to somewhat more complex is a butadiene, where we have 4 different carbon atom. In this case, we consider this case as the basic is using Schrodinger equation. What is a particle? The chance of the probability of finding the particle in 1 dimension box. We saw that. So that type of things, we found that there is a 1 node. If you have 1 atom, it's 1 node. If you have a 4 atom, it will give the 4 different nodes will come. And this is a different type of bonding and anti-bonding will give. So finally, when you have 4 atom acting together, this will be a distribution of your HOMO level. This will be a distribution of your LUMO level. Finally, we end up with the atom of, this is your band gap of your acetylene based molecule. Okay. So now we little bit go into the higher polymer. So far we seen about a very small molecule. What will happen when you have the multiple chain? So multiple chain, if you see that, so this is a very Schrodinger equation. You find the energy level of eigenvalue. This is a formula. So when you have the n number of atom, we don't know the carbon chain. We don't have n type of atom. So this will be the energy level of for n type of atom. For example, if you have a n type of atom, so if you have this is a 1 node. If you have a 1 atom, we have at least from 1 node. If you have a n atom, we have a n node of planes will form. So your HOMO and LUMO, the gap will continue exactly off place, n by 2. N by 2, if you have an n, half of the things node will be HOMO, rest of the things will be LUMO level. So if you find what is highest occupied molecular level, we'll substitute n by 2 in the energy level, and LUMO level is n by 2 plus 1. So if you make a difference of HOMO and LUMO, that will give the band gap. So here what I'm in this relation, what you can find is the energy gap is directly proportional to is 1 by n. Okay, it says that if the n number of atom is increasing, your band gap is decreasing according to this one. That means if you have a conjugated system of multiple molecules there, is the extended conjugation, will decrease the band gap. Got the point? So that's one is proved this from Schrodinger equation. You can say Eg equal to 1 by n. So that's why when you design the molecule, we need to have the increased amount of conjugation length so that we can get a required band gap. So it doesn't mean that when you have a, so we can have a question, if you have some thousand, then can you able to get a band gap of 0? That's not possible. But because when you have the multiple atom, there are a lot of interaction that a lot of other factor will come down. We cannot get 0, but we can have a minimum effect of low band gap. Okay. So like this, if you say that, suppose if you have the one single atom, you have a very large band gap, like n is increasing 1, 2, 3, 4, the band gap is slowly decreasing, and finally we get some of the things, some band gap is increasing. Okay. So this according to the Pearson signal, when you have the long band gap, there should be a distortion effect will be there. The distortion make it may not make it, the polymer is a more disordered state, that is doesn't allow to make it 0 band gap. It always maintains some of the band gap. So some of the ethylene and butadiene and acetylene, some of the molecule, if you see that by increase the conjugation length, the band gap is keep on decreasing. So one concept you remember that by increasing the conjugation length, justice will decrease the band gap of the semiconductor. So that's the only one. So this one. So this is a conjugation effect for designing the molecular materials. So other one is conjugation length. We already saw that. So what is the thing? So this is one of the molecule we designed in our lab. What we decide is this is a donor, and what we decide is this is a thiophene unit, and this is a donor. This donor molecule and conjugated length. Here we used n as a 0, 1, 2, 3, 4. Like this thiophene unit you increase, and end is the acceptor. When you see that by increasing the number of thiophene, which eventually increase the conjugation length, we can see the band gap is changing here. We can not only change it, this is a bigger one and keep on decreasing. So this effect is coming from because of this conjugation length. Okay. So and also you can say the absorption. When you have the green molecule, when you have the low band gap, we have the extended absorption. So by decreasing this one, and your band gap is increasing. Band gap is increasing, it's, your absorption capacity will decrease. Okay. So this will show you that how the conjugation will affect your absorption. Okay. Yeah, this absorption vector, yeah. Yeah, that's why I first explained, because I'm just showing the graph which I'm already explained. There's nothing. See absorption vector, same thing. That's why this absorption vector, when you have this conjugation length, if you increase the conjugation means low band gap. If it is low band gap means it will absorb at a higher wavelength. That's why if it is increase the conjugation is a low band gap, the band gap is very low here, for example 1.2. So we have the extended absorption. Okay, you have to now remember, if you have the low band gap, it will be extended absorption. Okay, if you have a high band gap, it will be lower band. It will, the absorption will be go towards you reduce the visible range of the absorption. Okay.
Why should we decrease the band gap? We are focusing on devices with higher wavelength absorption.
Yeah, no, we are showing that the conjugation. Sorry. Yeah. Right. Yeah, this is an example that how we can tune the band gap. This is one of the options. That's why in the design criteria, I'm talking about no conjugation. I'm coming to the some other effect also. So far I'm just explaining the theory. Now is actually experimentally we are seeing that so conjugation really affect the things. This is a synthesis and this is a observation. And also we have done a lot of device data when you have the longer absorption, and we can see the improved device performance as well. And this is another one. This already published in this work. If you have, this is a Riley-Nimide one. Here, this unit, conjugation unit, we change it to 1, 2, 3, 4. Then, when you increase this conjugation length, the band gap will be decreased. See, the absorption onset is going on increasing. You can see that. This also is conjugation length effect. And another, this polythiophene oligothiophene. If you have a 3 thiophene unit, we get a high band gap of 2.78. If you have 3 become 4, then you will reduce again 5 will again further reduced, and become 7, it always reduced. So by increasing the conjugation length, then band gap is progressively reduced. So this is a conjugation effect of making, and also this is a corresponding absorption spectrum of this molecule. Okay. So next thing is resonance effect. Resonance effect, I just talk you about how this the pi electron will be changing. How if you compare this one will take interchange from this position to this position, like this will change it. So this effect is called resonance effect. That's why when you represent the benzene ring, we normally make it this around the circle symbol, because this pi bond and single bond is always interchanging. This effect is called resonance effect. How this, if you introduce this resonance effect, then that also will affect the band gap of the material. In this one, so this is, we already showed that this one. So this material is particularly because of the resonance effect is very higher. That's why it shows the lower effect. Okay. At the same time, if you see this two molecule P3ST and the P3 selenium, because here it's a selenium comparing to the sulfur, the selenium is bigger atom. When you have this bigger atom, then ultimately the bond length between this carbon and selenium will be changing. So these changes will introduce into the band gap of this material. Okay, that's why in this case we are getting the absorption P3ST up to absorption 650 nanometer. So there we get the extended absorption of around 750 nanometer. So this is a PL emission for this material. We can see the change in band gap. Yes. Sorry. I said bond length is changing, right? Selenium is a bigger atom comparing to sulfur. So bond length is changing of bonding. So that's why I said when you have the CC double bond, CC triple bond is more. I said the length between CC double bond is 1.34, single bond is 1.54, and the triple bond is 1.20. That makes the difference in band gap. So the interchange, the CC bond length itself make an effect on band gap. Okay, that's one of the criteria. So next thing is substituents. I said remaining resonance effect. Substitution is here. This is not accepted. Here we have the different substitution end group. This is one of the indecenotyping acceptor molecule. So here we change this acceptor into different ITCC and different type of acceptor we attach to both sides. And how this molecule is changing, as you can see. So when you have the cyano group, these are more acceptor, CN group, 5.45. When we here introduce in this one ITCC, because here we have the methyl group here just remove the without methyl group, then it will, the HOMO level is pushing down. So in this one, instead of thiophan ring, we introduce the phenyl ring that will push further. And here the methyl ring we are putting into the meta position of CH3, that also makes change effect. And here we introduce a 2 fluorine group. Fluorine is a strong acceptor. So the strong accepting group also that is further pulling down, and fluorine and comparing to chlorine. Chlorine also is one of the high electronegative group, and also bigger comparing to fluorine is chlorine is a bigger atom as well. So see what are the different substituents causes affecting on the band gap as well as the HOMO and LUMO level of the things. So by changing the substituents of, yes, this all are, yeah, these all units are accepted. This we are attaching to here, accepted. Yeah, these all groups are we are attaching to A. Okay, then this whole molecule effect when I am so talking about. Okay, this A group means then whole thing how is affecting, because this is one of the well-known acceptor in organic photovoltaic. This is one of the high performance. Okay, low band gap acceptor. That's why I am saying that how the different substituents cause the effect on band gap of the material. Okay. Yeah, sulfur is electron, but in this case one, the cyano group take because double cyano group, that's acceptor compound. That will take in more effect compared to sulfur. Yeah, sulfur is good in conjugation, everything is good for the sulfur is electron rich group actually. But in this case only cyano group only, because this is called acceptor. If we take overall this moieties, the accepted the property is higher comparing to other one. Okay. So this, because so far I talked about conjugation and other things. Now these substituent also are getting effect. We need to worry about what substitution effect we got. We already see that this conjugation length, resonance, and functional group. Now we are going to see how the torsional angle. Torsional angle means there is a twist between these two atoms because of this electron repulsion between the hydrogen atom will be there, this twist. So that also cause effect on the band gap. Okay. So this will show that how is a twist occurring. In this one, you can see that this diaphragm one, because of this sulfur is interacting with the oxygen. Here is the position is not interacting. So the angle twisting at 2.7, but in this case, it is highly twisted, it making 74.9 high twisting. So the intermolecular interaction make the twisting is very long. If you have more twisting, that will break the conjugation, then lead to high band gap. Okay, this is one of the twisting option. The other one is you can say how the interchain effect. So in this interchain effect, we have the thiophenyl ring, we have a lot of chain things. So this chain thing, you see how well interdigited is aligned in this one. Because the chain group, the interchain, when you have is aligned one, so each chain will go to the void of the other two chain atom. Because in between chain, the next line, next backbone will come into in between the two things. Then it will make a very cyclic amount of arrangement will form. This is one of the STM picture of this how this arrangement is happening, and this is some of the structural arrangement of this type of things. Because when you have this make a film material, how is arranging on top of film surface, that will also affect your band gap of the material. Is an interchain effect. The other one is molecular weight effect. This molecular weight also. So molecular weight doesn't need what is a repeating unit of one another, because in polymer, how much repeating unit is according to the molecular. If you have many repeating unit, is a high molecular weight. So that molecular, how many repeating unit, that affect your band gap. Suppose we have synthesized this type of material with a different band gap, different molecular weight. So this different molecular weight, we have the different device performance. When you have the only 19,000, we got only 4.4 efficiency. Remaining everything is same. Only the current is different. When you have a higher band gap, the efficiencies go up. And when you have around 112,000 gram per mole, we have the best efficiency of 8.5%. Okay. So this is so that significantly the molecular weight also have significant effect on band gap. That's why currently we are using polymer, but getting a repetitive, so getting the finite molecular weight is too challenging. That is a synthetic challenge. That's why many group is moving towards the molecular material. That means the monomer material, so that we can define the material we can make, so that we can purity as well as the molecular weight, everything is we can define structure we can make. But polymer, this one of the issues is already there. So molecular weight also have impact on band gap. Okay. Okay, so far we have seen what are the criteria. So another things I want to see, donor acceptor concept. As I said earlier, when you have the good low band gap, we have another option is we need to alternative donor and acceptor. So this will cause the push-pull effect, because high rich electron rich compound will have the push electron, the acceptor is pull electron. This concept is introduced here. If you see this donor acceptor, this donor bithiophene one will have the 1.3311, and when you have the acceptor as benzodiazole, this have the energy level of 2.64 and 6.81. This one when combined together, we have the entirely new band gap, is reduced band gap. You see, this is high, nearly is more than 3 eV. This is only more around 2.8 eV. They end up with 5.2627 is a very reduced things. This is because of the donor acceptor point. Like this, we can also define many donor acceptor polymer to tune the band gap of the material. So this organic semiconductor is many types, either polymer or small molecule organic toners, or polymer acceptor material in the polymer acceptor or small molecule acceptor. Either it can be a polymer or small molecule. The polymer can be donor polymer or acceptor polymer. There are two things, P and N type. Each type we have a polymer and small molecule. So there are 4 different organic semiconductors we can define. Okay. So next it will give some of the idea about this many group, how we can this donor acceptor concept. This one I have seen that this is a band gap of 4 and 4, but when we combine together we got 3.9. Like this, we combined this dithiophenone and this fluorine unit and this one, then we can still 2.8. So like this, different donor acceptor we mix, we can change the band gap of the molecule. So this is the library of different donor acceptor material which reported in the literature actually. This one have different type of device performance. And this one will give you some of the donor acceptor material and corresponding device performance actually. These are all OPV power current efficiencies 9.4. Again, I come to the point, we are going to see how to characterize this photovoltaic cell or organic LED. I'm saying that this VOC, JSC, it may be new to you. So how to calculate the PC, that we are going to deal in, I think, second tutorial. That time you will get to know more about that. So this is some of the characteristic data to define how is the performance. Because, right, so PC is the main point. What is the power current efficiency? 9.4. Like if you have a, you know very well, silicon solar cell, if you have a 21 to 25%, this is the initial stage, 9.4%. Okay. And this is 10.6, and this polymer donor acceptor 11.3. And recently, in 2019, they got this polymer material will give the efficiency of 15.7, this organic 7. Like this, the field is very grown fast. Every time they're changing the designing of these molecules and getting finer and finer and get a good efficiency. And this is some of the acceptor. Acceptor means somewhat higher LUMO and HOMO level, this molecule. When you use this, IDTBR is 9.9, this is a structure. This ITIC then gave that 11.2, and ADA type, if you see all these molecules, acceptor, donor acceptor, I said previously introduced only a donor acceptor concept, and also not only donor acceptor, acceptor, donor, acceptor, donor, like this different. You see this is a acceptor, this is a donor part, this acceptor, all things. And if you see in this molecule, ADA type, this is acceptor, again this is thiophenone donor, this is benzothiodiazole, this is acceptor, again donor and the acceptor. Like this, these are all different designs. Like the enhanced push-pull effect, that also decrease further the band gap. So this effect, this band gap is very low band gap. That's why we are getting the improved device performance. When you go from ADA type to ADA type, the performance you can say 11.2 to 16%. You can see how improvement is coming out, all design. So this is about our ADA type, donor and acceptor compound. So what are all the acceptor people are used already? This type of acceptor, they attach to this, you see they put add bins, they replace with different type of acceptor, then different name they got. And these some of the library. I'm already explained what is the purpose of doing this one. I'm saying that there are huge libraries available, people already designed. Still from this library, we are selecting the best one to fit it what our requirements. From this one, you select the required band gap, then we can use it for our device fabrication purpose. Okay. And this is another small molecule acceptor, it's a donor material. Donor material, if you see that, as I said already, more on sulfur rich, that is donor material. If you see all sulfur, whole things. These are all different type of donor materials available. Then next one, this one have all today percentage Y6. This Y6 type band gap with the acceptor, donor acceptor concept. They have different variety of family in this one, reported one. So for all this material give the very good device efficiency. This one increase further efficiency to close to 20% now. Okay. These are all development is happened in the last 4 and 5 years time. And this is another concept for designing with the effect of resonant energy, the same as donor acceptor molecule. So these are all, I'm giving some of the example which you used to use all the synthetic the design factor, and they make different type of molecule in this one. So with this one, so this slide will show that even though we show that all the design, how to make this material, there's another question. That question goes to the synthetic chemist, organic chemist. Okay, so far we can design all the material chemist, we can do that designing, but only synthetic people only can synthesize molecule. I'm giving some of the method how to make this molecule. So the polymerization method is we can do electrochemical, and the chemical method is oxidation condensation. This is one of the different radical polymerization and CC bond formation. This is one different method used to chemistry. And in electropolymerization, people are making polyaniline, polypyrrole, and polythiophene. These are the polymer we can do electropolymerization. Electropolymerization, know the electrochemistry, we know that by applying electricity we can do that. And some of the CC bond, because in all these conjugated polymer, everything is a mixing of linking of a CC bond. Because in the pi conjugation, C double bond, C double bond, if you see the main chain, the core is, everything is a phenyl benzene ring or thiophene ring, it's a linking. Basically more is CC bond. This CC bond synthesis doing Suzuki polycondensation. Is it that will make using the brominated one monomer, and this is a boronic acid. It will link together, it will work the CC bond. Okay, there's a lot of mechanism inside this one, you will know. And in another one, stellate application, where we have the tin N group will react with the halogen group, bromine group, then this CC bond will couple like this. So this is some of the synthetic approach to make the conjugated polymers. Okay, this is some of the methods people do that. Yeah, I'm not going to detail about the synthetic method. So I think I'll give simple overview about how we can design simple what we need to consider, taken into account to get what band gap you want, and how it's going. I didn't go through the detail of synthetic method. That's not purpose of this one. What is the method is available? How to make the material, and after making this material, how to characterize minimum the band gap. What the things only band gap and co-mode one. That one is minimum criteria is UV and cyclic. There are not only this method. There are some other methods available to do this energy level. As I said, UPS and other things that will give IPS as well. But these are all very basic things, and in all chemistry lab you can find this instrument, and we can do that. Okay. So with this one, I will conclude this lecture, and next lecture tomorrow. As I said, I only show the only UV and this one how to characterize. There are some other methods available. Not only once you make energy levels, then we make a film. What morphology of the film want? How to arrange this film the way we want. So how to characterize the one? People you know very well about X-ray and other things and all things. All those characterization method, required method, we will discuss in the next class. That's it. Okay. So now we can ask if you have any questions about. Blend means is a physical blend or something? What is it? Yeah, that is that's I'm going to talk about in device fabrication, because when you make a photovoltaic device, then it's a PN junction, right? You need a P-type, N-type material. We need to mix together, then make that. I will talk about in third day lecture. Sorry, in so that plate is flexible. This is covalent bonding. We are making the synthesis CC bond with the donor acceptor. This is the design of the model. Finally, everything will interact. This multiple atom interact together, and finally we'll get up in some band gap, either P-type or N-type. So when you make a blend, we make a donor molecule, acceptor molecule, different ratio and mix it, then make a film and device. So that will come different. Your blend the blend doesn't change the band gap, but it will change the properties about. Yeah, surely the amount of blending also will affect what ratio you put it donor and acceptor. So 1:1, 1:2, that will affect the performance of the device. Yes. Yes. Yeah, these are all I think interchange used. Both are almost same. Absorption coefficient will tell you that how strongly your molecule absorb. The coefficient will tell that 10 power 5, 10%. That's all. Both are same well, but a different naming only. Same well. Yeah. No, DRS concept we use different. DRS we use for, I think, the powder sample, right? Powder. Huh? Yeah. Yeah, solid substance. Yeah, if you have a solution, that's different absorb, not DRS, but that method is different. I am talking about in solution phase and film phase. DRS we talk about powder phase. It's a direct reflection, yeah. That also give you the band gap, yeah. But in but hmm. Yeah, I, yeah, I'm coming to the DRS is good, right? We need to roughly know what is absorption range, but according to device concept, it's not a right concept because when you make a powder form and film form, the arrangements are different. How the molecule arrange pipets like anything, that will change the absorption property. Suppose if it is finely arranged, we can get a slightly extended, as I said, going from liquid to film, film to crystal. Everything is shifting right hand side. But in your case, because crystal is highly ordered one. When you have a highly ordered one, still we can have the low band gap, higher energy absorption, higher wavelength absorption, okay? But in powder stage, some material, most of the inorganic material, is very difficult to dissolve and make a film. That's why people go for powder method. If you can able to make a film, easily go for film. The powder we can take, okay, if you can't able to make a, it doesn't, because some of the inorganic material is ferrites, other things, it doesn't dissolve. People will, that's why particularly in using in battery performance, they make a slurry only, they can't make film. They mix with the slurry and they coat it. That's okay, we can micron, but in our OLED or OPV device, we can't work in micron. We need to have a 100 nanometer device. In that case, what you got to do is, you have to make a solution and make a film like this. We can't work on the thicker level. So for DRS film may not affect useful for our method, but for other purpose, for battery and capacitor, that should be okay. Because that application is different, okay? That we keep working on micron level. Yeah. Yeah, that's why there's, which slide is that? Yeah, molecular weight, yeah. What is your question? It's not an increase. Thickness is same. Here I'm saying that molecular weight also affecting the band gap and performance. I don't know, we are not we didn't see the band gap, but eventually it affects the performance of things, some slight changes. Because if, again I said molecular weight changes means number of repeat unit change. If the repeat unit is very high, molecular weight is high. If it less, so when the repeat unit is very less, the conjugation is eventually affected. With high molecular weight, the conjugation length is high. If it is conjugation length is high, slightly there will be difference in band gap. That's why, yeah. Yeah, that's possible. Yeah, when the crystalline formation over. Another thing is, as I said, band gap is reduced means the absorption will be extended. When you have more extended absorption, it's obviously the JS will be increased. When you have with the extended harvesting of light, the current will be increased. That's one of the options. That's why I'm saying that higher molecular weight is possible. But if it is too much higher weight, then again solubility become issue. We can't dissolve the material. We have the appropriate amount of molecular weight. Because we have a molecular weight of even 200, we got it, but that we can't able to dissolve. Yeah, right. But all this material PDA is between 1.5 to 2 only. We are not making PDA so high, 4 or 5 molecular weight. Okay. So that's different with PDA. Yeah. So any question? I think now is 3:10 is going for a break. Yeah, break. We'll come back and see the tutorial. As I said, tutorial we see. I'll give few problem 10 and see like CV and band gap, and you'll understand more. Okay, we'll see that. We'll come back 3:30 or something. 3:30 we'll come back. Okay.